everyone, it's Ms. Chen with a solution video to number 3 for your day 12 homework. So in this problem, we're given a solution of iron 2 chloride being mixed with a solution of ammonium hydroxide. So as usual, let's start off by writing a balanced chemical equation before we look too much further into the numbers. So since we're dealing with two solutions, we can assume that the iron 2 chloride is aqueous, and that's reacting with an aqueous solution of ammonium hydroxide. And so this will be a double replacement reaction. So let's figure out what the charges on each of these ions are. So we have an iron cation, so we're not quite sure about the charge since it's a transition metal. We do know that each chloride has a -1 charge, so since there's 2 chlorines and 1 iron, that iron must be carrying a 2+ charge to balance out the charge of the 2 chlorides, which each have a -1. Ammonium and hydroxide are both polyatomic, so you can look at the polyatomic table to find that NH4 has a +1 charge, OH has a -1 charge. Iron 2 will seek out hydroxide, forming FeOH2, since we need 2 of these hydroxides to balance out 1 of these irons. And we're going to get NH4Cl. We just need 1 ammonium and 1 chloride ion to balance each other's charges out. We know that anything that combines with ammonium will be aqueous. And then if you check your solubility chart, you can see that iron 2 hydroxide in fact forms something insoluble. So that's our solid precipitate. And then the final step is to balance. So we see on the left side, okay, there's 2 chlorines. On the right side, there's only 1. So I'm going to put a 2 in the front here. That means we now have 2 ammonium ions on the right side. So I'm going to put a big 2 in the front here. That's going to also now affect us. Now we're going to have 2 hydroxides on the left, but we have 2 hydroxides on the right. So I think we're in good shape, 1 iron and 1 iron. So we're good. So there's our balanced equation. And now we're ready to take a deeper look into the numbers that we're given. So we're given the volume and the molarity for each of the reactants. So it looks like we can go ahead and set up our molarity equation. Since we have the molarity and volume, I'm just going to write down these given values for each of the reactants first. And then don't forget, when you're using the molarity equation, you have to convert milliliters to liters. So to find the moles of iron 2 chloride, you can take the molarity, which is 0.335, and set that equal to N over 0.08555 liters. So to solve for the moles of iron 2 chloride, I'm going to take the 0.335 and I'm going to multiply it by 0.08555. And I'm going to keep 3 sig figs since 0.335 has 3 sig figs, 0.08555 has 4 sig figs. So I'm going to end up with 0.0287 moles of iron 2 chloride to begin with. Same process for the ammonium hydroxide. We take the molarity, 0.117, set up the molarity equation, and find out that we have to multiply it by the 0.1355 liters. So I'm going to do that right now, solving for N. And I get just about, let's see, I'm going to keep 3 sig figs again. I have just about 0.0156 moles of ammonium hydroxide. So we found out the initial amounts of moles of each reactant that we have. So let's look ahead and just see where we're going to try to go with this. So we're trying to find the grams of the precipitate that are actually produced if the percent yield is 74.5%. So this second part here, we're given the percent yield and we're trying to find the actual yield. So we're trying to find the actual yield in this problem. So the only way we can find the actual yield if we're given the percent yield is to find the theoretical yield. So this is where knowing the moles of each reactant comes in handy because now we can treat this like a limiting reactant problem. I'm going to just choose one of these numbers here, the 0.0287 moles of iron 2 chloride. And I'm going to see what we would need in terms of the moles of ammonium hydroxide if all of these moles of iron 2 chloride were to react. So I'm setting up a mole-to-mole ratio between the 2 reactants. For every 1 mole of iron 2 chloride that reacts, 2 moles of ammonium hydroxide are needed. So I'm going to go ahead and take the 0.0287, multiply it by 2, and I get just about 0.0574, and that's going to be my moles of ammonium hydroxide that I would need if all of my 0.0287 moles of iron 2 chloride were to react. Well, let's compare what we would need to what we actually have of the NH4OH, and we can see we would need 0.0574, but we only have 0.0156 moles of ammonium hydroxide. So it's not possible for all of the FeCl2 to react. So therefore, we know that the limiting reactant must be the ammonium hydroxide. Okay? So now that we found out this information, we know that we can go ahead and take the moles of NH4OH, the ammonium hydroxide that I have, and I can use those moles of NH4OH to help me find the moles of the precipitate, which is going to be the solid that forms, the iron 2 hydroxide, that can theoretically be produced. So mole to mole ratio, 2 moles of ammonium hydroxide will give me 1 mole of iron 2 hydroxide. And so if I do a quick 0.0156, divide that by 2, we end up with just about 0.00780. We have to keep 3 sig figs. Moles of iron 2 hydroxide that can theoretically form. Even though, it does specify that we want the actual yield in terms of grams of the precipitate. So let's go ahead and turn this theoretical yield into grams so that we can use the percent yield equation. So I'm going to take the moles of iron 2 hydroxide, and I'm going to convert it into grams of iron 2 hydroxide. And so that's going to be the grams per 1 mole. We're going to look at the periodic table. We see that the molar mass of iron, let me see here. Sorry, I'm looking it up right now, is about 55.85, I believe. Okay, good. So we have 55.85, and we're going to add that to the molar mass of 2 oxygens, which comes out to be 32 grams per mole, plus the molar mass of 2 hydrogens, which is just about 2 grams per mole. So we end up with a molar mass of about 89.85 grams per mole for iron 2 hydroxide. And we'll multiply that by 0.00780. And we'll keep 3 sig figs, which means we end up with a theoretical yield of about 0.701 grams of iron 2 hydroxide. So what we just found here, we just found the theoretical yield of our precipitate. Okay, so don't forget, these lovely stoichiometry calculations, we're living in theoretical land throughout this whole time. You're trying to show if everything went like perfectly according to plan in the reaction and all the limiting reactant gets used up, then this is the maximum amount of iron 2 hydroxide we can expect to make. But in reality, someone did the lab and was only able to obtain a percent yield of 74.5% of this expected value. So our job essentially is to find the actual yield in terms of grams of the precipitate. So the final step is going to be, I'm going to section this off here, is going to be to use the percent yield equation, which involves comparing the actual yield to the theoretical yield and then turning that decimal into a percent by multiplying by 100. And so we're going to end up with some value x that we're solving for, right? That's going to be our actual yield. We just found out from our stoichiometry calculations what the theoretical yield is going to be. And then we have to multiply that by 100. And then we do know actually the percent yield, which is 74.5. So sorry, that's supposed to go in here. I didn't line this up very well. So 74.5 should equal x over 0.701 times it by 100. So the first thing I'm going to do is I'm going to divide both sides by 100, and I'm going to end up with 0.745 equals x over 0.701. So to solve for my actual yield, I multiply both sides by 0.701, and I'm going to get 0.745 times 0.701. I'm going to keep 3 sig figs, and I'm going to find that my actual yield of the precipitate of the iron 2 hydroxide was just about 0.522 grams. So we just solved for the actual yield. So similar concepts in this problem, just a slightly different variation of what was given to you in this final step. You were given the percent yield and trying to solve for the actual yield. In the past problems in this assignment, you were given the actual yield and trying to solve for the percent yield. So just a slight flip of the algebra equation, but hopefully that helps to clarify if you had any questions. If it doesn't, feel free to reach out and I can definitely help you beyond just this video tutorial, but thank you for listening if you have, and I will see you soon. Thank you.